Okay, this is an introduction to rates of reaction. Okay, so we're aware of some reactions are very fast, like putting potassium in water. Some are very slow, like rusting, and everything in between, of course. Okay, and the definition of a rate of reaction is either this one here, the rate is equal to the amount of product produced divided by the time, or it can be the amount of reactant used up divided by the time. And if you want units for those, well, you can have, so amount of product, you can have grams per second, or you might want to measure it in moles per second. Or if you're measuring a change in concentration of the reactions in solution, then you would be moles per decimeter cubed per second. Rate and change of concentration. Or sometimes if you are measuring like the volume of a gas produced, well, it would be centimeters cubed per second. So it depends on the reaction you're looking at, really. Okay, now let's have a look at some examples of how to measure the rate of reaction. Some reactions are difficult to measure. So for example, if you get acid and alkali, mix them together, they'll neutralize each other, but it doesn't look like anything happens. You get two colorless clear liquids and mix them together and you get another colorless clear liquid, so you can't really see anything happening there. But some of the reactions that you use in class quite often involve reactions that make a gas. Okay, so you can measure the volume of gas produced. So a good example of that would be if you get calcium carbonate, which is a solid, and put it into hydrochloric acid, HCl, aqueous, you get calcium chloride solution, and you get water, and you get carbon dioxide gas. Now you can measure the volume of carbon dioxide gas using this. This is a gas syringe, and you could plot the volume of carbon dioxide produced against the time. That'll be one way of measuring that rate of reaction. Okay. Another way of doing that is you could if you didn't have a gas syringe, as you can just use this sort of setup here, where you've got a measuring cylinder turned upside down, and you've got water in there, and you fill up the measuring cylinder with water, and the gas produced bubbles up, goes to the top here, and you measure the volume of gas being produced. And you could do that with another reaction which makes so for example, magnesium plus hydrochloric acid, that gives you magnesium chloride solution, and you get hydrogen gas produced as well. So you can measure the volume of hydrogen gas. Instead of measuring the volume of gas that way, you could also do it this way. So here we have what we've got here. We've got our reaction flask. This time we put it on top of a balance. Now this is particularly suitable for the one that's making carbon dioxide, the reaction making carbon dioxide, this one here, because carbon dioxide is a pretty heavy gas. It wouldn't be so good for hydrogen because it's a very light gas and you wouldn't get much difference in mass. But what you do is you put the flask on top of the balance, you put a cotton wool bung in there that allows the gas to escape, but it doesn't it won't allow little droplets of acid to splash out. So any mass loss you get is due to the fact you are losing carbon dioxide. And it's quite convenient because you can press tear or 0 on the balance, and then you'll get a minus reading. Let's say like minus 0.15 grams. That means at that point in time, it's lost 0.15 grams of carbon dioxide. So they're the sort of ways in which you usually measure the rate of reaction in class. There are other ways. So for example, if you make a colored product, you can measure it. Here we go. If you've got a colored product, for example, bromine, so you're making bromine in a reaction, which is a reddy brown color. Bromine, you could use it for this reaction where you have 5 potassium bromides solution. That's a colorless solution mixed with potassium bromate, which is also colorless, and some sulfuric acid. You need 3 of those. That gives you 3 bromines, and that's red. Okay, in aqueous solution, that's reddy brown, and you'll also produce 3 potassium sulfates and 3 H2Os as well. Okay, and they're both colorless. So as the reaction proceeds, this brown color gets darker and darker, and you can measure that using something called a colorimeter. So a colorimeter is basically just, you've got a light source, it shines light through the solution, and then you have a detector, and of course the darker the color, the more light will be absorbed by the solution, less light will reach the detector. So you can measure the rate of bromine production being produced continuously in that way. Okay, let's go back to our carbon dioxide generating reaction again, and we'll have a look at some results. So this is the reaction between calcium carbonate and calcium carbonate solid and hydrochloric acid. That's going to give us calcium chloride, as we said, water and CO2. So we put on this axis here the volume of CO2 that has been produced, and this is time. Now we can see at about this point here, about there, the blue line goes horizontal. So that means no more carbon dioxide is being produced there. And that's because at that point the reaction has stopped. And the reaction will stop for one of two reasons. Either you've run out of calcium carbonate solid, or you've run out of hydrochloric acid. Let's say that we have run out of hydrochloric acid. Let's say that basically we are saying that the hydrochloric acid, the calcium carbonate is in excess. It's an excess reagent, yeah. And we've got hydrochloric acid. Now, if you think, what's going to happen to the concentration of hydrochloric acid during this experiment? It's going to drop because it's getting used up by the calcium carbonate. And at this point, when the reaction has stopped, the concentration of hydrochloric acid will be equal to 0. Okay, now we can see that this line, it's not straight, it curves. And you can see around that point there, it's going a lot slower. It's producing carbon dioxide more slowly than it is at the start of the reaction. So what can you say about what feature of that graph gives you the rate of reaction? We might be able to see that the rate is equal to the gradient of the reaction of the graph. So how do you find out the rate at any one particular point? Let's say that you're told to calculate the gradient at time t. You want to find out so what you would do is you have to, there's time t, and you have to get a ruler and you have to draw a tangent to that line. So a tangent to that, at that point would be, so I'd say would be about there, like that. So you draw yourself a tangent, right, and then you want to measure what's gradient equal to. It's equal to the rate of change in the y-axis, which in this case is the volume of CO2, divided by the change in the x-axis, which is time. So then you draw lines here, construction lines. Let's do them in red. Okay, so that is going to be the rate of change, delta sign for that triangle, of CO2 volume, and this is going to be the change in the time, delta time. So you measure those, and the gradient is going to be equal to, yeah, that one over that one. And you can see as time goes on that the gradient of that line becomes less and less steep. And that's because the rate of reaction is slowing down because the hydrochloric acid is becoming more dilute. And eventually the hydrochloric acid concentration is 0, and the gradient becomes 0. You've got a horizontal line because the reaction has stopped.